Morning. Everybody having a good time? Geez, we're loud in here. I'll try not to hurt your ears. I'm Jim Florwick. I'm a principal technical marketing engineer, and I have a meandering title on my slide, and we're going to cover a bunch of RF stuff. Is that okay? Okay. You're my people then. Do check into the WebEx app. I posted the slides that are actually going to be presented here today in the WebEx room. I'm like the world's worst on having my slides done on time, but it's because we're bringing new content. And I added a bunch of stuff last night around the 9179F that I think you're going to like. So it was worth going in and messing with the process, but do make sure you download the slides from there. The recording will have the right slides on it, obviously. We're going to cover RF excellence, kind of our theme here. And we're going to talk about dynamic channel access because AI RRM's out there, and now I've got that cloud-based service, which we're also going to talk about. What that means is that there's a whole bunch of people on the cloud side of things that have never been exposed to RRM. Anybody in here have a deep, long relationship with RRM? Anybody have me teach you how it works? They never got that benefit. So we're going to start doing some of that. We're going to cover DCA, or channel algorithm, because it's, once we walk through it, it's fairly logical. But it can be counterintuitive if you've ever seen channels change in your environment. Whoops. We're also going to talk about Wi-Fi 6E, and we're going to talk about AFC in particular. Anybody deploying 6E outdoors yet? Anybody worried about doing it? Okay. There's been a lot of confusion on it, and I don't understand how we got there with, Wi-Fi 6, 6E, then 7, and different specs. And stadium antenna, we announced that yesterday. The new one, Wi-Fi 7, so I've got some fresh data on that. And I'm hoping we got the time to get into Clean Air Pro for a little bit, right at the end, but honest confession, we might run out a little time on that, and I hate doing that, but that's the cost of me jamming slides in this morning. So please do join the discussion on the WebEx space. I'm not sure that I've got it monitored while I'm in here, but I do get every question, and I do provide answers back, and we'll keep an eye on that for a while. So if there's something that's unclear to you or something you need more information on, I can point you in the right direction. Let me know. So we kind of got this theme of RF excellence, and I remember when I first got to Cisco back in 2007, I was looking at the challenge of RRM and management and spectrum management, and I found out some cool things, that Cisco really had some solid data in their database that they were using to manage their networks. And you can manage a network. In fact, I'm teaching my replacement. That AI is going to be my replacement one day. And I'm also teaching some people to figure out when it's in a bad mood and lying, but most of the time it's pretty right. So data is everything. The quality of that data is going to affect the quality of the outcomes, and that's what we're going to kind of cover today and how we're using that. Previous sessions, we did cover NDP quite a bit. Cisco's RRM is still just a group of algorithms. The AI comes into how we're applying those algorithms and when we're applying those algorithms. But the algorithms themselves are fairly straightforward. We manage the channel, we manage the power, we manage the bandwidth, and we manage whether or not we're doing multiple 2.4 gigahertz radios or multiple 5 gigahertz radios. Wherever we can shove an interface that it's going to be beneficial, we try to trim out or add in now. The dynamic channel algorithm runs on the group leader. The RF group leader, in context, is either the wireless controller, WLC, that's running RRM, or it's the AI cloud. And if you're on the Meraki system, it's the AI cloud. So that becomes your RF group leader, and that's where all of the data is going to be collected, and we're going to look at all the data and make the decisions. What do we evaluate? When I'm listening and I'm sending NDP messages out, I'm on every channel that I have available to me, and I'm paying attention for rogues, noise, co-channel interference, whether it's my AP that's causing me interference, whether it's a rogue AP, and we bottle all that up in something called a channel metric. Now, we get RF distances from NDP. NDP is Neighbor Discovery Protocol. Like I said, this has been covered the last 2-3 Cisco Lives. I'd recommend going back to this session on the content and looking at the archived content from that if you want to deep dive in NDP, because it's a cool sport. We've changed it a couple of times. But essentially what NDP does is it broadcasts at the highest power, at the lowest data rate, so that I have the furthest traveling signal consistently. We normalize that across the bands, and what that gives me is even if I change configurations or transmit power, my neighbor list stays stable. It's a constant, right? I know where everything's at. I have a choice to put it on channel or off channel, and it gives me a really accurate read and a stable read of the environment. Primary difference on this, what do you do if you don't use NDP? You're using beacons. And the challenge with a beacon is, in my neighbor list, which reasonably down to about -75 is what I care about, in that neighbor list, if I change power on an access point and it goes below that -75 threshold, he's no longer my neighbor. And if I add one in, it becomes a neighbor again. And when you start to get a lot of APs on the network, when the density starts to build up, that gets to be a lot to manage. And you have to trim that. Advantages to it is it's light, it's fast, it doesn't cost a lot of data. If you're running it on a cloud-based system, it's a small amount of data on the shard. So that's why AutoRF was predominantly in cloud systems. Best practices for DCA. Well, there's a couple of things that you can set up in DCA. Typically what you want to leave on is noise. You also want to monitor interference. You do not want to monitor load. If you're still on a controller, this is still available on the controller. I've not been able to get that off the menu. Don't turn that on. It's not on by default. And then device aware. Does anybody know what device aware is? Turn it on. That's a modification to TPC. That's to transmit power. But what we're watching in here is that load. Or not the load, but we're watching the cost metric. And the cost metric is a complex signal-to-noise ratio that we, as we scan and we hear noise, if we identify that as a rogue or we identify that as us, we're looking at signal, we're looking at rogues, we're looking at code channel, on channel, all the normal stuff you'd be looking at for interference. And we wrap that up into a single integer. It looks like an RSSI value called a cost metric. And what that really is a compound signal-to-noise ratio. And then we put one of those on each channel. The lower that number, the worse that channel is. The higher that number, the better that channel is. And we start off, when we do a solution set, by choosing the worst cost metric. And that worst cost metric and its available neighbors, first hop and second hop, I'll explain that in a second, go into a solution set that we're going to build to solve for channel. Once we've done that, and we took the worst, we're going to reorder this, and we're going to take a random number. And the reason for that is back in the day, think about the old use case where you had 2.4 gigahertz out at a golf shack on the edge of your campus, right? And 1, 6, and 11 were all hosed out there. There was no good channel to put that AP on. If you ran a channel plan and you changed the channel on that AP, the next time you line it up, it's still going to be the worst AP in your entire infrastructure, and you're going to solve for that again first. So if we didn't randomize, we had something called pinning. And this is things that we discovered as we started to get, to big controllers where we had 50 access points on them. Anybody remember when that was a big controller? I do. It was crazy talk, man. So as things got bigger, we had to get better about managing it. We came up with ways to do that. One of the other things about RRM that I love is people oftentimes get wound up about how do we handle regulatory. And again, it's very simple. Anytime we are getting ready to run that algorithm, the very first thing it does is it goes to every single AP and it pulls the regulatory information from every AP. So if that AP changes in between RRM runs, the next time I go down, I've got the new regulatory when I pull that back. And that becomes the bounding for the solution set. And this is why on a single controller you can run multiple countries, because I don't look at the controller value. I look at the controller value for what it's allowed to support. But I look at the individual APs when it comes down to RRM, And RRM will not let me, I'm only going to scan channels that I'm legal on, and that's the channels that I'm going to have to apply. So it makes it impossible for the algorithm to actually assign something that that AP can't handle in regulatory unless you put it in the wrong regulatory. That's gotten harder too because we know where we're at now, right? So simple things that were built in. That flow chart still runs. I went back to, anybody see Vishal Desai's session in here? That's the name you should look up. He goes into the depth about how we apply the AI RRM and all those AI algorithms to these algorithms and what they thought about when they went into it. I like Vishal. He's a deep thinking guy. And he comes up with some good solutions and makes my life easier, which is another reason to like him. That process and DCA still operates the same way it did. It just has AI now to help it understand a little bit more about the environment and do things in a slower way. So when we start off a channel solution, that CPCI is the center of the plan. That's the AP that we want to target. To that AP, we add first hop neighbors. First hop neighbors are neighbors that know about my CPCI directly, and my CPCI knows about that neighbor. I see you, you see me. Then we add second hop neighbors. Second hop neighbors are neighbors that I know about as a CPCI because my neighbor knows you. We bound the solution set by only allowing channel changes on the first hop neighbors. So if I'm going to improve my CPCI's channel plan, then I have to do it with that solution set alone, and I'm not allowed to change my second hop neighbors. What that prevents is us expanding and having an iterative change across an entire campus. Even if I find a better channel for my CPCI, let's say I can improve its life, I may not implement it because the next thing I'm going to do is something called normalized cost cumulative function. That's a perfect marketing word right there, isn't it? NCCF is a goodness metric. The first thing we did when we went in was we had this goodness metric of this entire cell. Even though my CPCI had a bad channel, maybe it had no bandwidth whatsoever, but the rest of the APs in that cell are doing pretty good. Together, we've got a group goodness metric. And if I can change the channel of the CPCI without negatively impacting that group metric, and I'll take a little bit negative, but I won't take a lot of negative. If I'm going to tune down several other APs by forcing that in there, I might just shut that interface off if I have the ability to do that, and that's where FRA will come in. It'll just say, I don't have a channel for you. So we're not going to do it just because, and this is where we get into the rub, because I get people all the time say, well, that should have changed the channel. There's another thing that'll modify that. Sensitivity. So in a daily environment, it's a very, very bursty environment, right? RF conditions change all the time. You've got loads moving through the office. You get a new project moving. You have meeting days, right? So things change all the time. And if you let an RRM or you let a channel metric go out there and start changing channels every time it sees a little load on it, which definitely decreases its fidelity, right? You will have channels changing all over the place. And what happens when channels change all over the place? Telephones ring. People hate that, right? It's usually your boss first. So we can't do that. The sensitivity threshold basically says it's a hysteresis. So for instance, if my CPCI happened to be, and I can't, does this show on the other screen too when I do that? Awesome. Love this thing. Any rate, say it's 15 dB because I'm at medium, which is the default. If I come back, I'm going to represent that in an increase in cost metric that I can get out of that with that dB or that RSSI value that we call a cost metric. If I can change that channel, and I can change that channel and get at least 15 dB better fidelity or signal to noise ratio on that channel, and it doesn't take down the rest of the APs, then I'm going to change the channel, right? Anybody ever look at a channel in RRM and say, man, that channel should have changed and wonder why it didn't? Most of those reasons right there are why it didn't. Occasionally we get a bug in this stuff. It's usually pretty right, if you can walk back through it. So hopefully that clears up a little bit of the mystery about some of those processes, but it is well thought out. That was all there for 802.11a, b, and g. And then we got 802.11n and we started getting 40 megahertz channels. And then after that we got 802.11ac and we got the overlapping BSS. And now everything's an overlapping BSS up to 320 megahertz channels. Golly, all that changed. You'd wonder if RRM actually made the trip, wouldn't you? It did. So there's a couple more things to consider about channel changes and whether it's constructive, healthy, or not constructive. And in most environments, you're going to have overlapping BSSs, or when you get too many APs close together and you're starting to run wide channels, what combination of overlaps is productive and what combinations is not has to be considered. So if you take a look at how things are laid out, and I'm going to use 802.11n and 802.11ac just as an example. Trust me on this, this is the basics. How many of you know that Wi-Fi essentially hasn't changed? It is still the same Fi. We do a lot of creative, fancy things above it, but the basics are still the basics. You can't talk two radios on the same channel at the same time. It just doesn't work well. And all of this is intended to prevent that. So when we've got a 40, we've got primary and secondaries, the secondary 40, the secondary 80, we've got tertiary 80s now, or secondary 80s, I guess. I thought we had words for these things, but we apparently don't yet. One of the things that keeps this sorted out is contention. So that CCA threshold comes into play when we're thinking about these things. If you take a look back in the 802.11n days, and I remember the first time I went through this chart, and I talked to the engineers, and I said, oh, so the secondary has got a much better contention value than the primary. So the primary is sitting there at minus 82. If it can hear things, nothing, down to minus 82, then we get the go-ahead descent, right? The secondary only needs to go to minus 62. What that means is that the secondary is going to get a lot more opportunities to fire than the primary. And that was why they set it up that way. They wanted the secondary to fire when the primary fired. And then I learned the dirty little truth was in the first 802.11n chipsets, they really couldn't measure the secondary. They just triggered it. So if you were doing 40 megahertz, it wasn't really controlled flight yet. It's gotten a lot better. We got a lot better radios now. But then we did 802.11ac, and that got a little bit different bias because we also had secondary 80s to consider. And then you can see this has been carried out for Wi-Fi 6 and Wi-Fi 6E. So what that means is it's very possible to starve an older protocol. So we took a very good look at what it would take to do that and how we could avoid that in channel planning because that seems counterproductive. And we looked at several use cases, and primaries overlapping is always the best use case. Why? If I've got two primaries overlap, we're sharing the same messaging. I can hear you, you can hear me, there's no hidden nodes. As soon as you go to primary and secondary overlap, now you have hidden nodes. Not only that, you've got the contention values to deal with, and things get a lot messier. So the way this works out, if I had channel 40 and 44 on an 802.11n AP, and I had channel 40, well, that should have said 40 and 44 because they are misaligned. No, that's correct, 44 and 40. If those two can hear each other at a reasonable distance, minus 54, no problem. If I do throughput tests on both of them, I get about half the bandwidth on both of them. Same thing happens at minus 64. I get to minus 74 where they're getting a little further away, and look what happens. Because that secondary's got a lower contention and it's misaligned, the primary for the 802.11n is not winning contention in an equal fashion anymore. The AC radio does win contention. He gets 220 megabits, and the 802.11n radio gets about 10 megabits per second in on the side. You go back out to where they can't hear each other, everybody gets the full bandwidth. You do this again with the primaries aligned, you get the same results. So that's constructive. When DCA goes out and pulls these metrics, it now has to be aware of 20, 40, 80, 160, and 320 megahertz solutions. That's a whole lot of channels. So how it represents those channels is, again, looking at that cost metric, and that's exactly what you see. Uh-oh, don't push that one. First day out with the new presenter. Channel 60 has got a problem. And you see that 128? 128 is a very high score. That's a null. That's a please don't do anything here. It should be much lower than that. So what we're looking at is all the channels as we go through, and the way this is going to be represented ultimately, as it goes through every channel, it's going to put these together in channel groups, and it's going to represent the information differently, and we're going to bias those channels that are in that against the rest of the channels. So the way this is going to stack up is if for a 20, I've got channel 52, that's fine. For a 40, I've got 52 and 56, which are both fine. But look at what happens when I sneak into an 80 and I try to get channel 60 in there, and it takes the whole metric down for the entire channel width. And that's the biasing. We actually look at that construct and say, look, that takes so many points off the rest of them, and that's kind of how we keep it sorted. And this information is available on the back end. Whether you're using RRM, anybody ever used the wireless config analyzer and take a look at the NDP messaging? It's a lot of detail in there, and if you're getting bigger networks, and believe me, I'm in the same boat now. If you got 5,000 APs on a network, there's a lot of sorting before I can really read through it. But this stuff's all still in the back end, and we still get it out of AI-RRM, and I can get an answer on pretty much anything that comes out of AI-RRM. It does have to go to engineering sometimes now, but we'll get an answer. So does any of this matter now that we have Wi-Fi 7? Well, there's a lot of cool things in Wi-Fi 7 to bring us efficiency. However, MLO is the one that really matters to channel planning in my mind, right? And this is the one that came up right in December, just before Christmas. I remember hearing somebody at the BU say, do we even care about channel planning anymore now that we have Wi-Fi 7 and MLO? I'm an engineer, so I thought, you know, we should probably go test that and get some data, because I think we do. What this does, though, is it abstracts us from the hardware layer. It makes the client agile. I can put it on any band on the radio without disassociating and reassociating. That's pretty cool. So we're above that now, and it means that I can be very agile across channels. How does that impact us? Well, first off, MLO has got a lot of different combinations out there. Single radio, multi-radio. Anybody look into Wi-Fi 7 and MLO and how the clients are coming out the door yet? A lot of expectations. I would pay some attention to this, because it's going to come right down to which client you have. Single radio is going to do switch. It's a one-way link. Single radio enhanced is going to let you work it like a switch. It'll let you switch on each other band, but never simultaneously. Multi-radio, simultaneous is the best performance out there, or you can double up and do a non-simultaneous and do it all in one direction. So there's a couple of really cool combinations out there. That last one really does push some throughput. And there's a big difference between them. So keep that in mind when you're evaluating it. One of the things we can do is take a hit on a channel and just seamlessly move over to the other one. The user won't even know it. They'll just see maybe a blip in performance for a second. But you won't get disconnected. It won't stop the flow. It's amazing stuff. Question is that going to affect channel planning? So we set up a test. We set up a chariot. We had, I don't know, 20 clients on each side that were Wi-Fi 7. 2 Wi-Fi 7 APs set up, and we ran some traffic just to drive a load. We weren't really looking for throughput testing. By the way, anybody noticed how ridiculously easy it is to go over a gig on an AP these days? It's fun. We started off with separate channels for 5 gigahertz and 6 gigahertz, and the throughput, 2.8 gigabits per second, super easy. That was 20 clients on each AP, and we were just running some streaming video over it. 65 milliseconds latency. Amazing with that kind of a load. Then we went and we misaligned 5 gigahertz on the same channel, put it on the same primary, sorry, and 6 gigahertz still on separate channels. And we took about a doubling of the latency. And that makes sense because 5 gigahertz at that 40 megahertz is probably where my control traffic was going, so it's going to alter. That's going to be getting me contention. 6 gigahertz is wide open for the actual packets. So it cost me about half my latency, but the throughput, you probably didn't notice that a whole lot. Now, misaligning the primaries on 5 gigahertz. Look what happened to latency. So now we're like 4 times the latency. People were starting to notice, and that's because we no longer have control of that phi layer. We're noise to each other at that level. We're not coordinating. 6 gigahertz is still being used for the throughput, but it's only getting the activity when I can break CCA on 5 gigahertz. Finally, we misalign everything. Put for 5 gigahertz on separate channels with 6 gigahertz on the same channels. Cost me a hit. I get a little latency. I get a little hit in throughput. And then when I misalign everything, things get really ugly. So the answer is yes, it does still matter how we plan channels with MLO, and guess what? It's going to get harder. So, any questions on that, or just too many to come up with right now? Too much for the first thing in the morning? All right, stick around. We'll get a little lighter here. I got asked just before this for AI RRM if I was going to start covering more of the cloud stack. Or in with the on-prem. I've been doing on-prem and cloud now in this session, I think for a couple of sessions, and it's really coming around to where it's going to be kind of the samesies. RF automation. Anybody here run without an RRM of some sort? You still believe channel planning manually is the right way to go? Excellent. Occasionally that happens. My first thought is you must not have a huge network because that can get really painful with 5,000 or 6,000 APs. Most people don't, and it works pretty well, actually. In fact, if you don't have any more APs and you have channels, you really don't need it. You can just spread everything out, but most of us don't live in that world. Unified AI. We built AI RRM as a cloud-native service. So that was built as a cloud-native service in the AI cloud. And that's what opened up the door for us to be able to start doing some of this conversion that we've done. And I've been involved in for the last 3 years, bringing the Meraki team and the Catalyst team together. And this was the first thing that we went after because we literally could plug it in. Now, there's a little more work to do than that. Anybody in here running a Meraki stack? Good. On the Meraki stack, there's a couple of things. The Auto RF was looking at beacons, one. And that's one thing that we wanted to get to, was get it up on AI RRM, which came in. We put NDP in an R31.7, I think. So NDP's in. We've done stuff with the noise metrics. So there's been a lot of background work done with the drivers. And we're getting the same quality of information out of both stacks now. It just wasn't there on the other stack. It wasn't needed for Auto RF. So we are getting both sets of data now. And we've converted over, I think R32 is really where we're fully in, and we just went GA with AI RRM. In the architecture, and this is the Catalyst screen, but it runs pretty much the same. We've come from the controller, we're going to the AI cloud. Everything's anonymized, everything's encrypted. We've got separate data centers, of course, on every continent. So we've done a lot of work to expand our presence in the cloud. And I think Asia-Pac was the last one that got AI RRM for the Meraki side. But that was, I think that was last fall when we came into there. So the data is protected. What do you get with AI RRM over RM? First off, how many people in here are on AI RRM now? How many are thinking about it? Okay. Everything that I just told you about NDP happens every 10 minutes on the controller. And it happens every 10 minutes, whether you're running DCA every 10 minutes or not. What that means is if you freeze your anchor time and you put it on one of those 4 times a day runs, whatever time of day that is, the last 10 minutes of data that you collected over the air is what you're going to run the solution on. So if you do that at once a day and you make it midnight in your shop, then you are optimizing your building for midnight, which may not necessarily line up with what you need for noon. And that's one of the things that we were able to manage. Manual config, we've got automated AI assisted. I've got metrics in the AI now that let me take a look at things just like I do on the WCAE, and we can make decisions the same way. So I have a concept of density. There's minimal config knobs. My biggest problem with AI RRM, I taught a lot of people how to use RF profiles and manage everything. And there's a lot of people that don't want to let go of that. But I can tell you with sincerity, a lot of universities that I was worried about doing things like that, or hospitals, actually flipped over, and AIRM's been pretty good about figuring it out. We've run it in convention centers, and it's doing a good job. About the only thing I still have a problem with right now, and we're still working out how to do it, is ceiling height. So TPC values might get impacted. But that's in extreme heights. We've got better visualizations. We are interrupt cognizant. Reward-based decisions. That's a big word, isn't it? Reward-based decisions mean that we're actually driving metrics. We're looking at the outcomes of what we're doing, and that's what we're going to drive, whether we do another initiation or another run or further optimization on. And we can actually go in and pull down everything that happened every RRM run as a download file. So that's that file. If I go back, I can look at whatever downloads of the last RRM runs I want, usually 2 hours at a time or an hour at a time, 2 sessions, and I can ship that off back to engineering. They can tell me without a doubt what every AP said and why it said it. So we've root caused a lot of things that way pretty quickly. One of the downsides on Catalyst was you had to provision your controller. Now, there are 2 schools of thought in here. How many in here are willing to let DNAC or Catalyst Center manage their controller? There's some sketchy history in the background. I can tell you with honesty, in AIRM, we got a lot of the parity built into the RF profile, so it's a lot easier than it used to be. There's still some people who don't want to do that, and that honestly was my biggest adoption blocker for 3 years, was that we insisted that you have a provision controller. So that's gone away. We actually can do it now over the top, just like you do for assurance. Not sure how many of you have looked at it since, but doing it that way makes it a very, very simple workflow. We need to have the control channel in place, but you can bring it up on AIRM without having to do too much with AIRM profiles and without having to let it write everything over your controller, which, if you have a large infrastructure, can take some time. So this was released, and then right after that, the walk-me's got better. What I will say is if you haven't considered this and you're a Catalyst Center management person, keep an eye on this and take a look at the new releases coming up. There's a lot of work now going into the background on this to simplify further the workflow, which got a little convoluted because of places where, well, you got to break eggs to make omelets. So that's where it got. We're doing a good job on it now. Software matrix for the minimums is up here. We do cover everything, and you can officially, wave 1 and wave 2, we've still got 3700s in there too. So if you've got 3700s on your controller build and it's within AIRM, it does manage that. We didn't test it directly. I've got a lot of sites doing it. So it's not a reason to not do it if you have some still out there. AIRM for the cloud's the part that I got really engaged in here about 2 years ago. And this is cool because this was the first thing that we got to come down and say, differences stop now. We've got to kind of come up with some sameness because we feel like if we teach you how to use something on one stack, it should pretty much be the same on the other stack. I shouldn't have to make you go out and read new books and relearn all the jargon. So that's been the attempt. In a lot of places we made it. In some places, because of the structure of the dashboard, we had to change up how we do things. But the outcomes and the information that I can draw out of this are still the same. So we do have the cost metric. The dashboard looks very similar. Benefits. Well, we got 14 days of RF trends. Even though AutoRF had 30 days of data back in the shard, it was still operating off of 14, and it was still really operating off of the last 15 minutes collected. We just had visibility to what it collected, but it didn't have any ability to use that in the algorithm. So that's one. We do have automatic AI assisted. We've got conclusions now are coming out, or insights are coming out. We're working on that project, and there's a lot of them. Service segmentation by buildings, yes, you can. MR dashboard, very, very similar to the Catalyst, and there's more coming. Some of it's going into assurance, but there's a lot of visualization coming to us. It does maximize performance, and it does simplify everything. And it works. If you take a look at the dashboard components, what happens if you see a negative metric, right? Well, we're looking at a couple of things. We're looking at, one, because of the way the architecture was in the dashboard, I don't have to have a single AI RRM profile. So this is a good news thing and a bad news thing. If you turn this on your cloud stack, remember that it's going to use the RF profiles that you have there. And those RF profiles were probably put in there to solve problems that you have with AutoRF. So go back and consider whether maybe or not you should lighten up some of that and let AI take a look at it first. And it's been rare, but I've had one or two RF profiles that have conflicted, and it's pretty obvious when it does. You're asking it to do something here and not the other place we found it. We're trying to do better about identifying any of those problems. That's one of the projects that we've got going. All in all, this has been received very well. A couple of things you get, and this doesn't look that different from the dashboard without AI RRM. Trend-based. When you look at AutoRF, it's that last 15 minutes. That trend-based is whether or not I should be looking at something. Should I change something? Is that the right thing to change? And should I change it that much? So this gives us the advantage of that 14 days of data. Flexible radio assignment. How many of you are familiar with FRA? Anybody love it? I do under the right context. Come on. I remember when we had to go out and turn off all the 2.4 gigahertz radios all by ourselves by hand. Anybody love that? All right. You can run it carefully, but FRA has made a huge difference in the cloud stacks. There was not even the ability to go back and take a look at the neighbor messaging. So that's been a big boost. Busy hour. Busy hour calculation is important, right? And we do this automatically. We're looking at load on the network. We're looking at the number of users. We're looking at all the things that say a network's busy. The difference is in AutoRF, we have this. In AutoRF, if you turn this on, it simply doesn't make changes to the channel plan and to the power for the online day. Once it gets outside of busy hours, it starts running again. It's not running on stored data. It's not running on optimizations that it worked out during the day. It just starts running again. Where AIRM comes in is I've got that advantage of 14 hours or 14 days. I can go back, look at the busy hours. I can say, look, I think a better channel plan would serve that good, and I can implement that after hours. So it's analyzing what's going on during the day. It's making those changes in its head. Anything that it optimizes for your peak performance, it's going to implement that night. It's a very different thing. Sensitivity, we still have it. And sensitivity low in the coming versions, there were two schools of thought out there. We always thought, hey, power changes are probably good because you get people loading a room or unloading a room. There are folks out there that when you set it low, say there should be no changes, period, ever. Now that's what that does. So it won't make any changes. If you go to medium, medium's going to give you some power changes. It'll only do a channel change if there's a serious contention, right? Somebody adds an AP or you get something changes and you got two APs sitting on the same channel for some reason, it's going to change that channel. Lastly, AI channel planning. When you talk AutoRF, AI channel planning, comes right down to we can see a radar hit, we can see a jammer, we can see interference on it, and it gives us a way to automate. When you used to go in and do an RF profile and shut a radio down because you knew that one was just sitting in a corner of the building and it was getting pounded by DFS, right? You'd shut that off and take the DFS channels out of that one. This does that automatically. It also monitors it. It's going to look at it every 24 hours. If that condition continues to exist, it gives it another point. And it'll increase in severity to the point that it gets up to like a 6, and you won't see that channel come back into your channel plan for 6 weeks, 4 weeks. Once I'm clear and I don't see that condition, I'm going to monitor it for a day and see if that channel's still bad. As I increase in severity, it gives me more days to monitor it, right? So it's actually pretty intelligent. Goes back and it identifies that one AP that can't use that one channel, and it manages that in the background. It does that and more with AI-RRM. With AI-RRM, it also gets the DCA channel planning algorithm. And that makes a big difference because we can do a whole bigger set of APs, a whole lot more efficient with DCA. The other thing is, AI-RRM, I don't know if I mentioned this, does not run on the same shard that the dashboard does. That's where AutoRF runs. This still runs in the AI cloud. It has to. There's a lot more data, and there's a lot more compute power going into it. So it definitely has to be out there. I say that before I say, yes, it requires the advanced license, but it costs us a lot more money to run this too. So that's how that worked. Now, how can you use this? On the dashboard, it's getting much better, and there's a lot of stuff coming out. There were good announcements yesterday about the unification of the cloud dashboard, and there's a lot of people thinking on this a lot of the time now. Bringing this together and making it easier to understand, we've got the AI to go back and tell you what the likely problems are going to be. We can even model the thing moving forward. We're doing that on Catalyst Center, so that's still coming to here. But let's say you do get a health hit, right? First thing I'm going to be able to show you is whether or not AI-RRM was a good investment. I can stack that up against other networks of similar size. I can show you where you're at on it. And if I'm wondering about whether or not AI-RRM made a difference, I can go back to when I turned it on. And that's something we see fairly consistently, is those improvements. And I'll show you some examples of more of them. But that improvement comes in because it really does do a thorough job going through the channel plan and getting us as far apart in RF as we can be. The health metric. That health metric is broken out into 4 simple categories, and it's 0 to 100, right? I saw some hands earlier when I said anybody used the wireless config analyzer in here, but there's a health metric that's been in there that Javier Contreras created that we've been using in TAC and escalations for years. That's what got drawn up into AI-RRM. So if you understand the components of it there, and you can go look at each individual one if you'd like to, we brought it into here because that's how we understood it, and it's been a solid health metric. The things that we're looking at, neighbor and co-channel, side channel, there's several categories underneath of each one of these headers, right? So neighbors is one, interference is another, noise is another, and then the client side, right? Low RSSI. Typically, if you've got a good network, it's people walking off that network is what's causing low RSSI. I get a deflection in any one of these categories, I can actually go look at what caused that utilization, and I can take that, find the AP, understand what that was telling me, and take it over to my spectrum page, and you find out I got 3 APs on the same channel, so it was really angry for a reason. That's the direction we're trying to head with this. Does it work? Yeah, it works. We got adoption on the Meraki side that just like a hockey stick, and it took off, which is actually why I got more development resources on Catalyst Center. This has been a real hit, and it's taken on, there's a lot of big Meraki installations now, and this is really what's needed to get to that enterprise level, because AutoRF, like I said, it works great, smaller network, not a lot of nodes to manage. But once you start getting up into these super dense environments where you're down to 800 square foot cells, and how we carpet bomb everything now with 5 gigahertz and 6 gigahertz, you're going to need something a little more powerful to do that, and this does do the job. Some more stats on it. I'll let you read over those in the background later. Bottom line is, it's something you want to be looking at. Oh, Wi-Fi 6E, AFC, and SP. Did I mention I spend 20% of my week now talking to government affairs people and regulatory? It's a very, very, very vicious circle out there. The cellular people don't think that we should have all the spectrum. They go back and forth. I remember the first thing that we had was a memo from the FCC. It was a complaint about interference, and I thought it was funny because we didn't even have any equipment out there yet. We couldn't get it, nobody could. You remember COVID? Nothing shipped. But we had a complaint. So that's the lineup. Everything's got a GNSS built into it now on the entire product set. If you don't, the GNSS module's up there. GNSS is real important to AFC. And I'm going to talk about AFC today. Does everybody understand the difference and why you need AFC? We got LPI power. 18 dBm is our max EIRP. We can't go above that. Other people got much more generous grants. But if you look at their 500 megahertz of spectrum, they're not going to be running 80. They're not going to be running 160. They're pretty much stuck in 40. Because if you go to the ETSI model with 500, you get 2 more 40 megahertz channels than you do if you're in 5 gigahertz. So they got more power because they need to make the power in that first 20 megahertz. When I first saw this, I thought, man, that's odd. And I thought I understood it. Well, the other things we got with LPI was no outdoor, no 6 gigahertz for public or private. I got high ceilings in there. How am I going to get to the floor on that? And then you start taking a look at, while it's power restricted, it's good for indoor for 5 and 6 roaming. So where are we at? Well, it comes down to this. We can get more. And more is always better, right? Not really in radio. But you can get more. But where do you need more? And the reason we can get more is because there's 2 bands in there that still have occupants. And that's the Uni 6 and the Uni 8 band. And what you'll find in there is mostly TV, telemetry. I just learned something. We can't get it onto cruise ships. We're working through that. You know what the issue is out there? They use 6 gigahertz from satellite to measure the ocean level and the temperature. We're going to find a place to play nice out there, I promise. Any rate, I get more power. More power is good. Notice that 36 dBm with 21, if it's 30 degrees from the horizon, that'll come into play later. But that's not the first time we had that 30 degrees from the horizon. They're worried about the satellites. That's how it looks in PSD, real quick. Here's the issue. Anybody survey 6 gigahertz? Anybody go out, set it up to 160 megahertz channel and expect to see that beautiful 27 dBm? Some people did. And then they measured it at 20 and they found out it looks exactly the same at 160 as it does at 20. Where's your beacon? It's in 20 megahertz. You know what your limit is on 20 megahertz? 18 dBm. 18 dBm is your gating EIRP for an LPI cell. You will get 21, 24, 27, but only when you're doing data frames and you're doing multi-channels. For all of your beacons and your management transmit power is going to be 18 dBm max. And that comes into a problem when you start getting further away from the floor. Now, there's some good news here, and we'll talk about that a little more when we get to the high density discussion on this. AFC is a reality. If you're going outside, you're going to have it. How many people are wild about hooking up their regulatory domain to a regulatory domain? Comes with the territory. We're going to have to go to the internet to get AFC because we can coordinate it, and that's going to be the secret to us getting more spectrum shares in the future. It's actually been very useful to us here. We're tracking our data very well, and it's been very useful in going back and having conversations with regulators and sorting through some of the concerns. We need to, because there is indoor and outdoor you have to be very model specific. So the AFC database needs to know about the AP. It needs to know whether it's indoor or outdoor because there's different power levels. Indoors, I get a generous 6 dB building entry loss. That's a bell. Outdoors, I don't, and I have different concerns outdoors and more power constraints. They're also looking at how that propagates, right? So they need to know what the AP is capable of, the antennas on it, the height it's mounted at. The location is very critical because they're going to map this against interference profiles. And then you can configure all of this through the WLC dashboard or the Meraki dashboard. What does AFC need? Very, very specific information, and it's very strict on where you're at because that means everything, right? It's the difference between interfering with somebody who's an incumbent. How many of you occasionally go outside the law and you don't have to raise your hands, I'm not taking pictures, and maybe did something outside that, you might not have should have with a DFS rule or something like that? You can get away with that. Don't do this with 6 gigahertz. The guys that are in 6 gigahertz that you're going to interfere with know how to find you, and they will get a phone call back from the FCC. They spend a lot of money with them. So it's not a good idea. You definitely want to go through this. Why is an AFC needed? Well, because we have those incumbents out there, and Wi-Fi does interfere with things. And what we need to do is be told how much we can operate at and how we can do that safely. So if we know where everybody that we can interfere with is, we know how we're going to propagate to them, I can get a channel plan back from an AFC, and it comes back as a PSD, but what it's going to look like is a set of power constraints. And this is exactly how it's represented on the dashboard. It's very similar in the WLC. We're going to show you the power constraint and all the channels, and pretty much every place we've been in the US so far, I've had enough channels to make work what I need to work outside. You get into an inner city, it's denser, you're going to start seeing some power constraints. One of the things that you can do to ensure you don't have power problems is have a solid GNSS distribution system, because every AP that you have operating on AFC needs to have a location. The accuracy of that location is going to contribute to how much power you're going to get, because the more uncertainty you have, the more uncertainty that model has. Sorry. Drive location over the air, NDP or beacons. I can pinpoint an AP and its location in RF now. So if I have a derived location from a GNSS source, I can say it's at least this far from that GNSS, and that gives me an area of uncertainty, but allows me to distribute that on a system inside the building. If I only have one GNSS and I do the whole building, it can be very problematic. The other way we can do this is on a switch port. If you think about it, I can only be 100 meters from a switch port with an Ethernet run. So my derived or my uncertainty when I do it on a switch port is now 200 meters because it could be a maximum of 200 meters between my GNSS and my switch port. There's a look at the classifications. I threw this in there for information. What's the AFC going to do? It knows where everything's at. It knows a lot of detailed information about these grantees. So it has a very, very accurate model of what that installation can tolerate for interference and what it can't. And the bottom line is if your location puts you inside of any of those contours, you're going to get a power constraint. And it's going to be around whatever channels they happen to be operating on or licensed for. What causes an uncertainty? Well, how many people have looked into GNSS and ellipses and all the cool language that comes along with that? I did, because we kind of got into this. But that area of uncertainty is very literally just the range of information. So if I'm taking hits from a GNSS, I see it moving around. If you ever stood with a GPS unit in your hand, you've seen the little dot moving around. The entire circumference, or the ellipse that creates, is your area of uncertainty. It's an X and Y math function. And it says, I'm somewhere in here, which means my uncertainty area is this many square meters. And that's what they use for plotting it on the map. They just do a big circle with square meters. It matters. We had one of the early users, EFT, Luke's a great guy, University out here has been super for us. He had one 9163 with a GNSS outdoors. He had all 9166s with GNSS's internal deployed across his entire campus. No, he didn't have GNSSs in them. Didn't have them plugged in yet. He turned on AFC. By the time it got to the end of his campus, it was almost 2 kilometers. And he started to see some heavy-duty power constraints. So it matters. So if I'm going to deploy indoors, now my first problem is GNSS. How do I know if I've got a good GNSS? Well, that's directly from the module on the access point. And that tells you a lot of information. And I don't think I put a reference in here for the document. I did not. I will put that into the chat room. We wrote a document on this, on how to survey for this. Now, one of the things about GNSS is it's a mix of low Earth orbit and medium Earth orbit. The low Earth orbit satellites are going to change a lot. And they're going to change over the course of a 24-hour day. So when I first asked engineering, if I do a site survey for this, oh, you just leave the AP there for 24 hours. Anybody ever do a site survey? You got a week to check 7 spots? No. All right, what's that really mean? Well, for the purposes of a survey, right, we kind of did some logic and looked at some stuff. We did a lot of testing with this on campus. First off, you get better GNS inside of a building. If you don't have E-glass, you get better GNS inside of a building than you would think. The external antennas add a lot to it. If you can see 4 satellites, you can get a lock. That doesn't say you're going to keep a lock an hour from now. If you can see 6 satellites or 8 satellites, you're probably going to be okay. It's a fairly covered area. So that's where our conclusion came down to. It's a short sheet on what you need to know. Clients. We're seeing client counts go up all the time. And there is some variation in clients out there. You've got dual mode clients, and then LPI clients continues to creep, but it doesn't go up by that much. And the SP only clients are actually repeaters off of a set system. So there's not much out there that isn't at least thinking about it. There's more LPI than I'd like to see. But the worst case scenario is this. If you can't get on 6 gigahertz, you're going to fall back to 5 gigahertz. And that's still pretty good. The other thing we have out there for planning is our friends at Federated Wireless. That's a QR code. You can take that. You can sign up with them. And it is a free service right now. And you can go pinpoint anywhere you want to in the country. And I immediately, when we got this tool, went and looked at every major metropolitan area because you couldn't convince me that we weren't going to have a problem in there. It's actually not bad. We've got a bunch of sites out there in beta right now, and they're in a very big, dense areas. And we're getting plenty of channels to work with. So don't be afraid of AFC. Stadium antenna. How many of you heard the announcement yesterday or have been on the floor to see the 9179F? Man, I got to tell you, I've waited on this thing longer than you have. This thing's cool. When you got high capacity, you need directionality. You got to separate those APs. This is the way to do it. And this is the 4th generation of this building. The challenges, they're in 2 stadiums that are built alike. There isn't 2 conventions. Well, convention centers tend to have a lot more stable lines. But stadiums, you don't know where you're going to mount. You're going to be a hybrid mount, under the seat, over the seat. Everyone's just a jewel. It's a fresh painting. The way we used to do this, a couple of Gillaroos, 9120, we're still doing that here. We did that on 3700s. We went up to 9120s. So we've had a couple of generations using these antennas. Gillaroo was our 2nd generation. Anybody see this? Yes. I knew I'd find a room full of radio heads that had looked up already. Anybody know what that antenna's for? BLE. Know why it's there? Because those directional antennas stink for location. That's exactly why. And we actually ruled that not supportable for location, and then people who had convention centers turned it on anyway and said, geez, we're getting really bad response here. So that was the solution here. Dave Benham put all that in for us. Any rate, large public venues, 9104. Anybody use a 9104 yet? Real quickly, why we thought we could build a better one. This came out, it was the first purpose-built with the AP built into it. its strategy was to be good everywhere. One of the things that kills you with directional antennas is ceiling height. What happens when you raise it up? It gets bigger. When you put it down, it gets smaller. We made it beam steering. We did that so that you could use the same AP and use it in multiple places. Side benefit of that is that has a beautiful wide mode. If I have narrow running for high density, when I empty out these halls, I can flip a third to a quarter of them on wide, and I can still cover the entire hall and save all that power. Beam steering, we had multiple ways to beam steer. It was actually too flexible. We had 10 and 20 degrees off the center, independently adjustable by each side. A lot of you guys loved it. Some of you came back and said, man, that is awful confusing. Why you give me so many choices? Does it work? Well, that's a keynote in Amsterdam. We had good traffic in there. Take a look at the signal to noise ratio coming from that floor, and this is coming from telemetry on the client. This is not something I'm calculating. I've never in my life seen signal to noise ratios like this, except under a 9104. Truss was at 18 feet. It was 6 meters. Yeah, you'd think you'd be burning the hair off of people down there, but you weren't. You weren't. I mean, that's a dense environment, man. There was a lot of people in there. But yes, it works. So we thought, hey, this you can look at with an eye chart later, but that's left and right 5 gigahertz balance across it, and they're actually fairly even all the way across. So we've learned a few things about this. But Wi-Fi 7's out there. What are we going to do with 6 gigahertz? It's a whole new game, right? Well, meet the 9179F. The 9179F, along the same lines of the 9104, different antenna design. And I got to tell you, Naveed did a heck of a job designing this thing. We've been really happy with it everywhere. So these are primarily the slides I changed this morning because I just got from Matt Schwartz, the Bottle Rock Festival, and all of their data from that. And I thought, he did it in a presentation, but you guys deserve the very best and the very latest. And I'll give you some more detailed information after that. Isn't that pretty up there? The other thing we know about doing shows, because we do a couple of them, we show up here 4 days before the show, we throw a rack in there and we just swing all the cables over and start putting in extra APs. So there's a lot going on. When you start talking about mounting antennas, if you need to redo a keynote, there's a lot going on. Well, we've also got things going on with the 9179F that you're going to want to use this indoors and outdoors. And that's a problem that they had to solve. And they were talking with the FCC and our compliance folks about how to solve that. And they came up with the idea with this weatherproof door. So that AP without that door is not weatherproofed, and it has a power table for indoor LPI power. Once I put that door on it, it has silicone gaskets and everything else. It becomes a weatherproof seal. We have an or a prom in there that's going to tell it that it's an outdoor. So I actually get 2 models of APs. There's an indoor and an outdoor model of that just by switching that cover. You don't have to order 2 APs. You just have to have that cover. The other thing we found out, and this was when they went out and installed the first ones, was that a guy standing on a lift at 100 feet. Anybody ever stand on a lift at 100 feet? If you ever do that, don't look shocked because that's what the rigger's looking for because it bounces constantly. Every time you breathe, every time you move, it's just like this. So now you're up there with a cover and a cable and silicone gaskets, and that doesn't feel good, does it? So we made an extension cable so you could put this together on the ground because we just want to get in and get out as fast as we can. The mounts on the back of this are VISA, so you're unlimited as far as mounting actions. Typically when we're putting on an AV rail, we put the hardware right on the antenna. Everything's pre-staged. We go out with a whole trailer full of these things and we just hook them on the rail. And then they do the lift and we plug everything in before they do the lift and hopefully see if it's working. I had a couple of guys recently that thought it didn't matter. They got on big ladders. Another thing that we got a problem with the 9104, anybody ever put one up against the back of the wall? You've got a dead zone right underneath of it. You've got a dead zone behind it, and that's not always convenient. A lot of times you're at the top of a bleachers or you're in a corner or something like that. There's still seating in there, and you'd like to get some signal down to it. So the third mode of operation, there is bore sight, there's wide, and then there's this front and back. Front back takes 2.4 and 5 and puts it out the back on these directional antennas, believe it or not. And it gives you that fill-in, and it's intended for small spot coverage behind that antenna. and it works like a champ. So that makes it super flexible. There's all the stats on it and the beam shapes. Why do we do this? Anybody ever deploy a stadium? Okay. Typically, you're going to find it's going to be a mix of underseat and overhead. And there's a crew out there that believes underseat's the only way to go. And what happens when you do underseat? Everything is contentious. Everything's co-channel. If you look at that place when it's empty, you couldn't believe Wi-Fi'd ever run there. When you put all the water bags in, it soaks everything up and you start to get some separation, right? Problem with that is, now I'm radiating through people. Common wisdom says you're going to lose 3 dB per row, right? That's generally the guideline on design. What does that mean? It means that every time you get another ring away from that AP, your performance is significantly different from the person in front of you, and what you end up with is a very lumpy cell and an unequal performance. And I don't like that. It's messy. What you're seeing on the left is co-channel interference. Well, I got to point it left. Co-channel interference is what all that red is. Those are APs crossing there, and they're co-channel level, and that's a timeline going to the right. On the right is what happens if you're overhead. We get extreme isolation, and it actually looks good when it's empty, and it looks good when it's full. When it's empty, I'll see a lot more neighbors. When it's full, everything still tightens up. What that is pretty equal performance across that entire cell coverage. And if you've ever sat, anybody was in the keynote yesterday? Those were Gillaroos in there, I think. Anybody have problems with the Wi-Fi? I'm not in the Nokias here, so it'll be a surprise to me. It's DNS was so it wasn't the RF. Design goals, these are the typical designs that we've got out there now. I've got the 60-degree and 70-degree inbuilt directionals. We've still got the wide antenna. That thing's beautiful in a hallway or a warehouse. And now the 9179. The goals for this were what we just kind of covered. The deployment flexibility, the indoor-outdoor integrated unit. These are things that we know we need because we're doing this job. On the controller, you can see what your antenna angles are. You can also see it on the dashboard. This is cloud, and it is on-prem. Balancing 5 gigahertz. Balancing 5 gigahertz is absolutely key. Anybody ever put 2 5 gigahertz channels over a group of people? If you got an inequity in the power, you will wind up with all of them on one or the other. If you want them to spread out, it has to be as close together as it possibly can be. We know this because we did it wrong. Now we do it right. Low band, high band, 5 gigahertz gives us really, really solid isolation. This is a very, very high gain environment. You need the isolation. Remember that 30 degrees from the horizon? How would you know if your antenna was pointed within 30 degrees of the horizon unless you go out and measure it? Same 100-foot lift, got your iPhone out on the front of it trying to guess at the angle. Or you can look at it on the controller of the dashboard. We put an accelerometer in it. We did that for a couple of reasons. Anybody ever deploy a bunch of antennas and then come to find out when they're walking through and see that antenna got banged by a rigger and now it's pointed up to the sky and you got a dead hole in the middle of it? That'd alert you to that. Somebody asked me yesterday, said, hey, can you get alert on that? The answer is yes, we could alert on that. We don't yet, but we could. You have to enable the accelerometer. It's not on by default. Now, does this work? Now we know. We've got it out there in beta. We did a couple of things before that. This is a place called Claire Audio up in Lititz, PA. They're a big user of our equipment. They do a lot of stage shows. They do audio and they do stage builds and they train guys on their campus. And they have this big, beautiful building that goes to 75 feet high and has these lovely 8x8 square chunks of concrete on it that you can do an amazing site survey in. And the best part is it's 20 degrees and cold as hell outside of that building. And in here, it was 70 degrees, and there might have been a beer in the fridge. So we got to put the 9104 and the 9179 right next to each other on that rail, and we went out and took a bunch of measurements because all of us were anxious to see whether or not that antenna was going to work, and by God, those patterns looked beautiful. This is the installation at Bottle Rock. Josh Schur and Matt Schwartz were out there, I think just 2 weeks ago. Josh did a survey in narrow mode from the front of the stage, and then he did one in wide mode. And that's the coverage he got. And then he picked a spot out here at the sound booth, which was smack dab in the middle of that massive crowd they had out there. I think Green Day was on stage at that point in time. Josh calls that his chewy gooey center right there. And he did a 6 gigahertz speed test on that from there. That ain't bad for sitting in the middle of a crowd that's streaming. This thing absolutely delivers over the distance. Mounting options are very flexible. Like I said, that's a Visa bolt pattern on the back of that. Make sure you don't go too deep. You don't want to break this. We did some testing with the 9104 right up against the 9179 out on a range that we built off of one of our office buildings where we had some distance. 2.4 gigahertz coverage, you're looking at the Marlin 4 on the left and the DB10 on the right, which is the 9179, 9104. 5 gigahertz coverage patterns. That was left. That's the high side. Low side. That's the steered on the left side. And that's 6 gigahertz. That's 6 gigahertz just about maxed out right there, by the way. 6 gigahertz power. Does that look like it might be a problem to us? Think about this. In 5 gigahertz, if you've done high density, you know that we need to get the signal noise ratio up, and the only way to do that is to get the signal over the noise. And we have a lot of noise in 5 gigahertz. And I kept hearing people say 6 gigahertz was going to be quieter, and then I talked to Matt Schwartz about that. And I said, do you really think it's going to be that much quieter? And he said, yeah, man, there's no probing. And he's right, I forgot that. There isn't any probing actively in 6 gigahertz, and it in fact is quieter. And I've got this running in convention centers now in Europe. I've got it in a convention center. We've done 4 or 5 events there already, and I'm not even running full power. So they're doing all right on 6 gigahertz. We'll see if that holds up. 6 gigahertz adoption hasn't been there yet, and I do know that there are several people clamoring to get a chunk of that space. So we're going to get interference and things that aren't Wi-Fi in 6 gigahertz eventually. It's going to happen. They're going to keep pecking like ducks until we get a crack. Which brings us to Clean Air Pro, because we're going to get interference. And we've got cool tools to work with it now. And the reason I threw this back in here, Wi-Fi 7. We actually finally got preamble puncturing. I can take chunks out and keep transmitting even if I've got interference, if I can identify the interference, and I can, so that's cool. So this is already engaged. How many of you are familiar with old Clean Air Pro, or Clean Air? How many of you are running Clean Air Pro? There's not as much interference now, right? And now that concerned me because the things that we were looking for when we ran Clean Air were a whole bunch of stuff that operated in 2.4 that doesn't exist anymore, right? Everybody had Wi-Fi now. Nobody wants to produce anything that interferes with Wi-Fi. You can't sell it. So Clean Air's job was to identify non-Wi-Fi interference specifically because a Wi-Fi chip only knows if something is Wi-Fi or not Wi-Fi. And if it's not Wi-Fi, it's only noise. And noise is not all created equal. If it's man-made noise, we can probably avoid it, or we should probably go remove it. One of the things that we did, that we still do, is something called clustering. And our competition never got onto this. It's one thing to identify a signal, but unless you can identify that signal from that specific device, every time you hear that signal on an AP, it's another instance. So if I got 15 APs in a room and I flip on the Bluetooth receiver or transmitter, 15 APs report Bluetooth. Do I have 15 Bluetooths? I don't know. If I've got 15 Bluetooths in a room, which one of them's the worst? Can I track the individual metrics of it? No. So how is that useful information if I can't cluster it and say, look, this is the same device. Here's the loudest one. Now I even have the information to locate it. And that does still work in Clean Air Pro. So we came off of the ASIC and we went back into software primarily because I got so many cores in the AP now. We can actually run this up as a software routine. It used to take very specialized hardware. So we still do the clustering. And when we say clustering, we mean give you one alert and actually tell you where it's at. And that still happens in spaces. So if you've got clean air and you've got an identified interference source, you'll be able to see that on a map in spaces. Actionable information. On the controller, you can go take a look at the cluster ID, and the cluster ID is going to show you anyone that has the same cluster ID says this interference incident is part of that. And if you go drill down on DNAC or through spaces, you can get very detailed information still off of the type of interference source and whether or not we think it's good or bad. In clean air, we've got a goodness metric. So here's the thing. I was with Cognio. We had this little tool that you put on a laptop. It was very innovative at the time because people didn't like to think about doing anything but 2.4 gigahertz, and we'd already gotten too dense to make that usable. And then all somebody had to do was bring their toy to work, and we'd shut down half a network. Apple actually released a release that shut down half a network one time. 2.4 was fragile. We didn't have a lot of spectrum. We were able to look with that laptop, identify an interference source, and we were able to get a very accurate AQI. We didn't have an AQI, but you could look at the duty cycle and tell which one of these interference devices was your problem. You could actually use it to locate it. When we put this into every access point, now we've got a different problem. I've got an AP that might have multiple interferers on it, but how do I represent the goodness or the badness of that collection of interference? And that's where the AQI came from. And this is really simple. We start saying that the spectrum is 100 points. And then everything that we detect, we put a severity rating on. Severity rating, did I go to the right? Sorry. Severity rating comes in with a couple of points if it's higher duty cycle, if it's higher RSSI, if we're seeing it in multiple neighbors, that increases that severity metric. So if I had 5 Bluetooth devices, all of them with a relatively low severity of 2, I would take 10 points off the AQI and represent the total diminishment of that cell. So that's really where AQI comes from. And it comes right down to the number of interferers, and the severity of those interferers is how you're going to see that deflection. Something in here called persistent device interference. Persistent device interference is things like that microwave in the break room that's going to take out channel 6 every day at about 11 o'clock to 1 o'clock and then start again at 3 o'clock with the popcorn. Every time that microwave goes off, channel 6 looks good again, so RRM might just go ahead and put it back there. Clean Air sees that microwave, tracks it for 7 days. Every time it sees it, it resets the bias number and keeps that channel from going back on that AP. When it doesn't see it for 7 days, it drops the bias, and if that channel's better, it lets it go back to it. So persistent device interference should always be on. Event-driven RRM is the other thing. There were use cases where you get a video camera or a bridge or something like that that's going to consistently take out 100% of that AP's capacity because it's going to block transmit. When we see that, the AP has permission to get out of there. It can change within 30 seconds of detecting that. EDRRM works, it's effective, you can leave it on all the time safely. Reason that's relevant? Because I can see interference better, and this is a nice mitigation tool, and it's already linked back into it. So you're Wi-Fi 7 ready with Clean Air. What's coming to 6 gigahertz? Boy, there's all kinds of proposals out there. Anybody working regulatory or any of the comments that are going on back and forth between the industries? I get to see this. Bluetooth wants to come there. 320 megahertz channels for personal AV goggles. Oh, there's all kinds of arguments going on. One of them, VLP, they wanted to go to 21 dBm, and I said, great. Very low power has 6 dB more, than LPI. So there's a lot of conversations come on. Do I think this is going to become relevant? Yeah, I do. If you haven't seen preamble puncturing and work, go take a look at Nicholas Swiatekki's presentation. He did a really nice demo on it. It's amazing to watch. He's been playing with a lot of spectrum. We went back and did a demo on this. This is EDRRM, and this at the time, all I could get was a camera from a drone that would make a very small signal on the left-hand side of a very not so okay spectrum analyzer yet. I've got an Aronia ordered, but apparently we keep making drone detectors and I can't get enough receivers to do it. So, EDRM works. If you throw it up there, it'll change channels instantly. Please do fill out your surveys, get into the room, let me know what you thought of the content. If you've got suggestions for it, I read all the comments. I thank you all. I'm going to give you 10 minutes back. I hope you don't get angry with me for that. But you didn't ask a lot of questions. I hope that was good. And enjoy the rest of the show. Go out in World of Solutions, look at the 9179, and have a great day.